not a worksheet, a note sheet for you. Oh, I also have an announcement. Did you do the elementary STEM Olympiad in elementary school?
Yay.
Yeah, did you do that? No? Say someone was it. If you want to judge crypto or set for the STEM Elementary Olympiad, you can do that either on May 8th and or May 9th. But if you sign up on this link, it's a school excuse absence. They give you lunch. If you need, they can bus you there. Or I think you can drive wherever it is. So if you're interested in doing that, I have some flyers. I also have it posted up there. You just register at this little link. Okay. All right. Okay, let me handle this. Note sheet.
I watched every time it says that. Oh, they didn't do it at all. No, but I remember doing it in my elementary school. Ruined my class.
All right, so we are taking what we learned from the previous chapters on organic chemistry, and we're just adding to it. So today we're going to talk about how to name if it has a double bond or a triple bond. And then this is the trickiest part of this chapter, is identifying the rigid parts of a molecule. And we'll practice that in Alex at the end. And then we're also going to talk about how to identify an isomer, a constitutional isomer. Okay, so we've been using the ending ane for alkane, like pentane, hexane. That means it doesn't have any special bonds. Today we're talking about alkenes. So the ending is ene. They contain at least one carbon-carbon double bond. So they have a general formula of the number of carbons, and then the number of hydrogens is related to that. You just multiply the number of carbons by 2. And that's if it has just one double bond. Okay, so around a carbon with a double bond, if we're looking at this, then this is trigonal planar because we have 3 groups around the carbon. We have 2 hydrogens and then this double bond. So anytime we have a double bond, that bond angle is 120. So this is an alkene. Alkenes have a double bond. Okay, the other type of bond we're going to talk about today is an alkyne. So this Y&E tells us the molecule has a triple bond. And then they have this general formula, number of carbons, and then the number of hydrogens is related to the number of carbons by 2n minus 2. Let's see, so if we're looking at this molecule, this has a carbon-carbon triple bond. The bond angle is 180 because the carbon has 2 groups. It has a hydrogen on one side or a different carbon, and then a carbon. So if we have a triple bond, that is a linear molecule, or that part of the molecule is linear. Okay, alkenes and alkynes are part of this group called unsaturated hydrocarbons because they have less hydrogens than you could fit on the molecule. So it's unsaturated with hydrogen. So an alkane would be saturated with hydrogens. An alkene or an alkyne is unsaturated. Have you heard that before? Unsaturated. Okay, good. Okay, and then this is just a note. When you're going from our normal uncondensed structure to a condensed structure, we're going to keep the double bond to show that there's a double bond so that we can see that. We can figure it out with the number of hydrogens, but to be really clear, we want to keep double or triple bond in our condensed structure. Okay, questions, thoughts, comments so far? Okay, so we're using the same template, the same pattern for naming. So before we used prefixes to name the branches, so we had something like 2,4-dimethyl. That prefix tells us the branches. And then we had our parent, the longest carbon chain, so like pentane, hexane. Now we're going to start using a suffix. So the suffix we are talking about today is "ene" or "ine," Y-N-E or E-N-E. So that suffix is going to tell us where is the double or triple bond. Or not where, what, do we have a double or triple bond? That's our functional group today. So don't forget what we already learned. We're just kind of adding to it. Okay, so then I think you have some of these rules. So for the parent chain, what we're going to do is we're going to number, so just like we've been doing, but if we have a double or a triple bond, this rule overrules the other rules. We're going to number to make number from the side that's closest to the double or triple bond. It doesn't matter if there's branches. The double or the triple bond wins. Okay. So this one, this we would number from this side, 1, 2, 3, 4, instead of 1, 2, 3, 4, because the double bond is closer to this end. So we could number this way, the branch would be at 2, but we are overriding that rule. We're going to go with reduce the number on the double or triple bond, the multiple bond. Okay, and the other one, there's another example. So this one, we have a triple bond. We're not going to start over here, 1, 2, 3. We're going to start over here, 1, 2, because we want that triple bond, the first carbon in the triple bond to be reduced. So start at the end closest to the double or triple bond. Okay. All right, so then these are the rules in your box. We'll just go through them really quick. So you're going to identify a number of the main chain. We've already done that. So figure out the longest chain that includes the double or triple bond. Reduce the number. So start with the side that's closer to the double or triple bond. If it's equally spaced, then you can consider the branches. So first pick the side that's closer to the double or triple bond. If it's equal, it's like in the middle, then go from the side closest to the branch, the first branch, the first substituent. Okay. We are going to put a number right before the parent chain to tell us where the double or triple bond is. If the double bond is in the first position, then the 1 is optional. I usually put it just to be very clear, but that is optional. Okay, we'll look at some examples. And then you name the parent as an alkene or an alkyne, depending on if it has a double or a triple bond. And then you're going to add a prefix for all of the substituent groups. So just like you've already done. You already know how to name all of those side chains, the side branches. Okay, questions? Okay, try to name these molecules. See if you can name these. So I'm going to point out, this is a carbon. So remember, if you have a triple bond, it's linear. You're going to have a carbon, 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 carbon. Let's go ahead and try to name those. Okay, are you ready to talk through some of these? Okay, what did you get for this one? We'll start over here. What should this one be called? So it has 6. Oh, 1, 2, 3, 4, 5, 6.
1 hexylene.
Oh my. Yesterday the finger was working. Now look. Let's see if I can more. Okay, none of them are working. Let's maybe have to turn the pen on. This one is hexine or 1 hexine.
Is hexylene.
So remember, this is our suffix for this triple bond. So hexyne or 1 hexyne. Oops, I don't know. Let's change this. Okay, are you okay with that? So we've got 1, 2, 3, 4, 5, 6 cards here. Okay, how about this one? What did you get here?
Excellent.
Hexene, okay, and this one we have to specify.
2.
Good, this will be 2 hexene. So this one, either option is fine. If we say hexyne, we just know it's at the 1 position. This one is not at the 1 position, so we have to specify. So this is closest to the 2 position. Okay, 2 hexene. E because it's a double bond. Okay, and then this last one, what's this one?
2
Hexane.
Good. 2 pentyne.
Oh, yeah.
Good, because we have 1, 2, 3, 4, 5 carbons there. Okay, does that make sense? Okay, so these ones didn't have any branches, so let's try a few with branches. Okay, so try this one. All right, you have a name back there. What do you call this one? Or
2 methyl. 2 butene.
good. Yes. So ENE because there's a double bond. It's at the 2 position, and I agree with you. We should go this way instead of this way because either way the double bond will start at 2, but this way we reduce the methyl. So good. I agree with that. Okay. You see that? Okay. Great. So we're just adding on to what we already know. So hopefully it's pretty straightforward. Okay, let's try one more of these ones. This one's a little bit. Try this one. Yeah.
4 chloro.
So let's see. So count for me. See at 4.
Start from the C.
This one?
Mhm.
Okay.
1,
And
2, 3, 4. Oh, you don't have.
So that, yeah, you only count carbons. Okay. Okay, and then we want to reduce the double bond. So,
Then up each one like that.
okay. Yeah, so we're good. 1, 2, 3. Okay, now ready?
Then it would be chloro.
Yep, and we will put the 1. Chloro. Okay.
Then would be 2 methyl. Or would you do?
Yep.
2.
So it can either be the chain or it can be a branch.
Okay.
So we're saying this is the longest chain. So that methyl is part of the chain. It's not part of this branch. So just a 2 methyl. Okay, keep going, Corbin.
And then 1.
Yeah, it's 3. What's the 3 one?
I know that's what I forgot.
Propane, and so then change the end.
Propane.
ENE. Propene. ENE. Good. Okay. The double bond is a double bond position. The other way we could name this is we could do the same thing, 1 chloro, 2 methyl, and then we could just call it propene. And just drop out this chunk because the double bond is at the 1 position. I like to put the 1 just so I I'm really clear. I know where it is, but you don't have to put the one. That's for sure. I think most of the time Alex will accept both. The programming is, there's like one of the questions that it only accepts one of the types, and I can't remember which type. So on the test, I will accept either of these, but you just have to figure it out on the homework what Alex will accept. Okay, I think we've got this down. I would like you to try to draw these.
Is it a skeletal or?
Yeah, you can draw either way. Yep. Yeah, this one didn't specify, so you can draw either way. Okay, are you ready? Is there anyone who wants to draw the top one for us up here? You ready? Do you want to draw the top one? Skeletal or condensed, either. And use your finger. I think that's been working better. Okay, very good. So we've got 2 chlorines on the first carbon next to the double bond. It's 1 propene. You have 3 carbons in the chain and another chlorine at the third carbon. Okay, that looks good. And I also like that you've gone through and made sure that each carbon has the correct number of hydrogens. The first one is bonded to 4 things already. The second one has 2 carbon bonds on the left, 1 carbon on the right, so then it needs that hydrogen. And the carbon at the end also needs 2 hydrogens. So that's, if you're drawing the condensed structure, that's really important. Okay, thanks. Is there somebody who wants to draw the 3-methylpentine? Anyone? No one? Okay, I can draw this. Let's see. So we have pentine, and if there's no number, that means the triple bond is at the end. So we'll try to draw the skeletal structure. So this is 2 carbons. Then we have another carbon. We have 5. 1, 2, 3, 4, 5. And then 1, 2, at the 3 position, we have a methyl group. So 1, 2, 3, 4, 5, and then our methyl. Do we agree with that? Okay, all right. Okay, very good. I didn't put that on it. Okay, this is the trickiest part of this chapter, I think. So we'll go over one of these together in Alex. Let's come back to this topic, actually. Let's talk about constitutional isomers, and then we'll come back and do that one. I'll switch it in my slides. So today we're going to talk about constitutional isomers. On your paper, there's examples of isomers. So constitutional isomer is, so an isomer in general is just a different molecule with the same formula, but it has a little bit different connectivity. So constitutional isomer, these are different molecules, but they have the same chemical formula. They both have 3 carbons, 4 hydrogens, 7 hydrogens, and bromine. but where the bromine is different. So in this molecule, one bromine, bromo, same thing. We have the bromine at the 1 position. This bromine is at the 2 position. These are different molecules. They have different physical properties. They behave differently, but they have the same chemical formula. That's an isomer. So you have to identify if something is an isomer or not. So this is the question that I ask when I'm trying to decide if something is an isomer. So check, do they have the same chemical formula? If they are, they have the same chemical formula, but they are in fact different molecules, there's different connectivity, then yes, they are isomers. If they don't have the same chemical formula, they can't be isomers. If they are the same molecule, so if it's just a mirror image of a molecule, or it's rotated and it's just flipped or something, if it's the same molecule, it cannot be an isomer. That's just the same molecule. Okay? So these two are examples of deciding if they are isomers or not. So the top one, so when I do this, I write out the formula, and then I look at it and I say, does it have the same chemical formula? Is it the same molecule or not? So the top one, what would our chemical formula? How many carbons, how many hydrogens? Oh, and I'm using my finger, I forgot.
5 carbons.
Okay, 5 carbons, 1, 2, 3, 4, 5, and how many hydrogens? So there's 3's on the end. How many?
12.
Yep, so 3 plus 3, 6, 7, 8, 9, 10, 11, 12. Okay. If this is hard for you to see, you could also uncondense it. You can do CH3, this is a CH2, 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 CH3. So if the skeletal structure is hard for you to look at, then uncondense it. Okay, how about this one? How many carbons, how many hydrogens?
4 carbons.
1, 2, 3, 4, and then 5. And then hydrogen, you have 3 plus 3 hydrogens, plus 3 is 9, plus 2. And then there's 3 carbon bonds, so there's 1 hydrogen. So there's also 12. So do they have the same chemical formula? Yes. Are they different? Yes. Okay, are these isomers? These are not isomers. Why are these not isomers? It's just a mirror image. If we look here, if we just take this molecule and flip it on top of this molecule, it's the same molecule. They do have the same chemical formula, but it's the same molecule. That's not an isomer. It has to be a different molecule to be an isomer. Okay, this is a little bit of a tricky topic, but I think this other one is harder. So let's go back to this. So what we're looking for is which of, in the Alex topic you're looking to see, in your head you're imagining the bonds rotating, and you're trying to see if the bond, the distances will change or not. So I have the model here, and it's an okay model. So let's see, let me see if this will work better. So if I have a carbon-carbon bond, so this is a model of a carbon-carbon double bond. So you see that's a double bond. If I have a double bond, it's a rigid part of the molecule. It can't turn. It's locked, okay? So if I have any groups, let's pull these ones off, around the double bond, so if I'm looking at this hydrogen and this hydrogen, the distance between these is locked. It can't rotate. The distance here cannot change. Okay, and that's what the Alex topic is going to ask you. Anytime I have groups on the same atom, so these hydrogens are going to be locked so this distance is not going to change because they're attached to the same atom. Okay, so anytime I have groups attached to the same element, those distances can't change. And then this distance can't change because it's blocked around the double bond. Okay? If I have a single bond, Let's try this one. So this is a little bit tricky because it looks like a double bond, but this one is a single bond. Single bonds can rotate. Okay, so let's see how much easier that is. So the hydrogen-hydrogen distance is going to be able to change because I can rotate around a single bond. So this is a little bit of a tricky topic because you're taking something that's 2D, and you have to imagine which of the bond angles can rotate and how that will affect the distances between the angles, or the distances between the atoms. Okay? So these are some things to remember. The bond length is not going to change, so it's not going to like all of a sudden grow, and that will change the distance. No. The angles between bonds coming from the same atom don't change. So like, even if I'm spinning this around a single bond, the distance between these two hydrogens is going to stay the same because they're attached to the same atom. Okay. And then remember, molecules can rotate around single bonds, and they cannot rotate around a double or a triple bond. That's stuff. Okay, so let's look at this Alex topic. If you want to pull out your Alex topic to work on this too. I think this is, for me, it's just a really kind of confusing topic. We have to look at these molecules and decide what's going on.
If I get 2 points on it, I'll be back in 70%. I'm going to be failing in class. Every month I grade 14%.
Okay, chapter 13 has 8. You're right. 8 topics.
I looked.
You looked. I didn't look. Very good. 8 topics. Okay, so this topic is called identifying rigid parts of an acyclic organic molecule. That means it's not a cycle molecule. It doesn't have a ring in it. Okay, so we get something like this. And I have some molecule kits. If this is really confusing, I had some students last year that it helped them to build a molecule and then just spin it. You can't do that on the test, so you keep that when you're in homework. So what helps me is to look at, if there's a trapezoid, so like this one, we have a carbon-carbon double bond. And so the distance between these hydrogens that are attached to adjacent carbons on a double bond, this kind of forms a trapezoid. These ones are locked. That's not going to do. This question is saying list all the distances that can change. So I just have to look at these red arrows and go through and think about what can rotate, what can't rotate, which bonds are going to change. So this one makes this trapezoid, so double bond, hydrogens. This E cannot change because the double bond is blocked. Okay, so that one can't change. Okay, let's go to D. If we look at D, this is a single bond, so this can rotate. So that's going to spin. That can flip the hydrogen. This hydrogen can come out of the page. So D can change. So for mine, I'm going to put D. Okay, let's look. C, can C change? This distance between oxygen and hydrogen?
No.
No. Good, because they're on the same atom. So this carbon is connected to the oxygen, the carbon is also connected to the hydrogen. If it's connected to the same atom, that can't change, so we don't write that down. How about B? Can the distance from this oxygen to this oxygen change?
No.
It can change. So if we look at this bond here, this one can rotate. So if we're spinning that, then this oxygen can come out of the page. The hydrogen, these actually could flip spots. So yes, B could change. Okay, next one, the last one is A. So we're looking here, we have the distance between this hydrogen and this oxygen. So if we look at this bond can flip, this can spin. So that's going to change where the oxygen and the hydrogen are. So if this is spinning, this oxygen can rotate out of the page, and get away from the hydrogen. So A can also change. Okay, does that make sense?
What can I say? What can
Okay, do you want to do one more together?
I say?
Yes, okay. More practice. All right, so this one, let's see, let's start from A. So over here at A, can this distance change? Well, if we look at this one, that's going to spin, that's not going to help us. But if we go one more away, this OC bond can rotate. So if this rotates, then the hydrogen here can get away from the other hydrogen. So because this can rotate, these hydrogens can change distances. So A can change here. Okay, the next one is B. Can B change? B is blocked. You're right, because this is one of those trapezoids. We have a double bond, and then we have two groups off of that double bond. So because we have this trapezoid, this is blocked. Okay, how about G and F? We'll do those ones. They're like very similar, right? We're looking at the oxygen to carbon bond on this carbon. Is that going to change? Same atom. So oxygen and carbon are attached to the same atom, so they can't. This distance is not going to change, so same with F. Those can't change. Okay, how about this C?
So closely related.
This one can't change. Good. We have this trapezoid again. We have the double bond, and then we have the carbon to carbon, carbon to carbon. So these can rotate, but the carbon distance is not going to change. All right, how about the end-to-end distance? So this is on a double bond, but if we go back to this single bond, this can rotate, so the nitrogen and the hydrogen can flip spots. So D can change, and so if D can change, then also E can change because of this bond here. So this is rotating, that can flip the nitrogen and the hydrogen. Do you see that? Okay, so I do think this is a little bit of a tricky topic, but kind of once you get the hang of it, it's not so bad, but it's getting to the part, to the point where you can start recognizing those is a little bit tricky. Okay, questions for me? Okay, all right, you have half an hour left of class. If you haven't done class 34, make sure you turn that in. If you need to return it in, do that also. If you haven't done your signature assignment, don't forget about that. We have, that's a whole 10-point assignment. And you're not gonna wanna work on that when you're trying to study for the final, so try to get that out of the way. And then also work on chapter 12, the deadline is Sunday. Okay. Questions for me? Is it doing all right? Okay.
We're back in the room. What is this?